Welcome to my channel. I am Dr. KP Naidu. In this lecture, I would like to discuss about what is meant by curse of dimensionality and what are the solutions for curse of dimensionality. Okay, so let us first try understanding what is meant by curse of dimensionality. Let us assume if our data set contains more number of features. For example, if a data set contains 100 features of 150 features or maybe sometimes 200 features. So if our data set contains more number of features, that is called as high dimensional spaces, clear, it is very hard to analyzing that data set. It is very hard to analyzing, it is very hard to visualizing, and it is very difficult to draw the conclusions from that data. That phenomena we are called as curse of dimensionality. Clear? So that means if you're having the more number of features, if you're having the more number of features in our data set, okay, making the model extremely slow. Okay, so that phenomena we are called as a curse of dimensionality. So now the solution for curse of dimensionality is, so we are trying to reducing the dimensionality, okay, by using some of the techniques. Okay, let us take one scenario. Let us assume MNIST dataset. Okay, in this MNIST dataset, we are having around 70,000 what is called as images. Okay, so each and every image with the size 28 by 28. That means 28 pixels in rows and 28 pixels in columns. That means 28 by 28 means we are having around 7084 pixels. Each, if we are assuming, if we are consider each and every pixel is one feature, that means each and every image having the how many features? 784 features. So if you want to visualizing the okay entire data set with 784 features, if you're having the, if you want to visualizing the entire data set with 784 features, okay, it is very hard to analyze, visualize and draw the conclusions. Then what we have to do? We are trying to decreasing this number of pixels. So how we can reduce this number of pixels? Let us take as this MNIST dataset. It is digit dataset. That means the dataset contains the digits from 0 to up to, we're having up to 9. Okay, so let us take as this is one image. Let's take as some 0. Okay, so let's observe this 0 can occupy this space. Okay, let us take some another image with digit 1. For example, if you take some another digit, okay, let's do. If observing these images, okay, with some digits, okay, the border of each and every images are not useful. Clear? Let's say these these pixels are not useful. This is the one. Okay, the border pixels are not considered, not useful. Okay, if you want to if you want identifying the two, this image border pixels are not useful. That means if you are removing that border pixels, there may be chance to reducing the dimensionality. Okay, that is one approach to reducing the dimensionality. So if you are reducing the dimensionality, then it may be easier to visualizing and to draw the conclusions from the data set. Okay, that is one of the example of curse of dimensionality. What are the solutions? How to mitigate? What are approaches to mitigate the curse of dimensionality? The first approach to mitigate the curse of dimensionality is reducing the, that is called as dimensionality. That is called as dimensionality reduction techniques. Okay, in this we are having different dimensional reduction techniques. Those are called as principal component analysis. Okay, that is and TSNE, T distributed stochastic neighbor embedding, and linear discriminant analysis, that is called as LDA, and autoencoders. These are the some of approaches, okay, to reducing the dimensionality. Okay, so in this lecture we are mainly focusing on how to reducing the dimensionality with the concept of PCA. Clear? So there are also some more mitigations, okay, approaches to mitigate the curse of dimensionality, that is feature selection, regularization, random projection, okay, data sampling or aggregations. There are so many there. But in this lecture, I would like to explain how to reducing the dimensionality using the principal component analysis with the technique called as PCA. Okay, so let us try to understanding in some mathematical way, okay, how the dimensionality is reduced with the concept of principal component analysis. Let us first try to understand in a mathematical approach, then we are trying to understand the implementation part of PCA. First, how the PCA works means, for the given data set, first step is standardize the data set. Then to the data set we have to compute the covariance matrix. Then to that data set we have to find out the eigenvalues and eigenvectors. Then we have to sort the eigenvalues and select the principal components and then transform the data set. These are the 5 steps we are following to find out the principal components. Okay, so let us start understanding one by one step. Okay, so to standardize the data set, here we are using one feature, that is called one formula, that is called Zij equal to Xij minus mu j by sigma j. That means this is one formula to standardize the data. For example, let's take as our data set contains 3 features. Feature 1, feature 2 and feature 3. That, and again we are having, let us assume 4 records. How many records? 4 records. Okay. So 3 features with how many records? 4 records. Record 1, record 2 and record 3, let us assume, and the record 4. Clear? So now we have to standardize each and every cell value by using this formula. Xij means what is the value we are having in this feature minus the mean of this feature by we are calculating standard deviation of that feature. By that formula, we have to standardize the cell value. Like this, we have to standardize each and every cell value by using this formula. Okay, so here xij means the ith observation of the jth feature. That means first row observation value, first row observation, first row value of first feature, this cell. This is first row second feature value, like this. Mu j is the mean of the particular feature. Standard deviation, we are applying the formula square root of 1 by n minus 1 sigma I equal to 1 to n xij minus mu j, mean whole square. That is the formula for standard deviation. By applying this formula, we have to standardize each and every cell value. That is the first value. That result we have to maintain as a matrix with Z. Okay. Then what we have to do? What is second step? We have to calculate the covariance matrix. The covariance matrix formula is covariance of, let's take as 2 features, feature 1 and feature 2. Let's take as 3 features. Here we have to calculate in the covariance of f1 f2, again f1 f1 f2, sorry, f1 f1, f1 f2, f1 f3, again f2 f2, f2 f1, f2 f3, again covariance of f3 f1, f3 f2, f3 f3. Like this we have to calculate the covariation among, sorry, between every pair of features. The formula for covariation matrix is 1 by n minus 1 sigma I equal to 1 xi, the observation particular feature value, minus mean of that feature into yi, another feature particular observation value minus mean of that feature. Okay, we have to multiply that one. Okay, and then sum. Okay, then we have dividing with n minus 1. We are getting the covariance between two features. In general, this covariance matrix is used if you're having the less number of the features. Okay, so if you're having the more number of features, if you're having, for example, 4, 5, 6, 7, or some 100 something, so if you're applying this formula, it is a little bit difficult. Okay, so at that time, for m dimensional standardized data, the covariance matrix C is defined as 1 by n minus 1 into. We here already got the standardized matrix Z like this from the data set. Then we have to transpose that Z. Then we have to multiply Z transpose with Z, and that can be multiplied with 1 by n minus 1. Then we are getting the covariance matrix. Covariance matrix. After calculating the covariance matrix, we have to compute the eigenvalues and eigenvectors. How to calculate eigenvalues? So to eigenvalues is from that we getting the covariance matrix 1 minus lambda I. Okay, then we have to some vector v equals to eigenvector v equals to 0. Here C is the covariance matrix, lambda is the eigenvalue. Okay, I is the identity matrix. I is the identity matrix. Okay, for example, if it is a 2 by 2 matrix, the identity matrix is 1 0 0 1. Like this, we are getting the I value. So we know the covariance matrix, we know the what's called as identity matrix, then C minus lambda I that can multiply with V equal to 0. Okay, so after C minus lambda I equal to 0, okay, from that we may getting some eigenvectors. So before calculating eigenvectors, first we have to calculating the lambda values. Lambda means eigenvalues. Okay. So to find out the eigenvalues, we are using the equation det of C minus lambda I equals 0. We have to calculating the determinant of C minus lambda I. Then we are getting the which one? Lambda values, that is called as the eigen values. Clear? So in example, you're clear understanding how to calculate eigenvalues, eigenvectors, covariance matrix, all those things. Once if you're finding the eigenvalues, arranging all the eigenvalues in some descending order. Okay, so if you are having higher eigenvalue means that particular feature is a more important feature. Okay, next higher value is another next important feature. Like this we have to understand. Okay, so from this, after arranging the all the eigenvalues in descending order, we have to select the top k eigenvalues to determine the number of principal components. For example, we are getting the lambda equals to 3 eigen, let us assume 3 eigenvalues. Okay, so from these 3 eigenvalues, if we are choosing, if we are, for example, after descending, after arranging the 3 eigenvalues, for example, 0.8, descending order, then next one is some 0.6, the next one is for example 0 point something 0 1. That is these are three eigenvalues. Okay, so here I can pick the two eigenvalues. That means we have to choose a two principal components. Two principal components. Higher eigenvalue means it is the most important principal component. Next higher value is it is next most important principal component. By using these eigenvalues, we have to calculate an eigenvector by using this formula. Okay, so how we are calculating, we will understand in the next example. Once if you are finding the eigenvalues and eigenvectors, then we have to transforming the data. Okay, the principal components are obtained by the projection and projecting standard data onto the which one? Eigenvectors. That is z dash equal to, we know the z, that is standardization matrix, that can be multiplied with some eigenvectors. Okay, that is matrix of top k eigenvectors. Then we are getting the Z dash. This is called as transforming the principal component data with a new data. Okay, that is called as the transforming the data set after pick the number of the components. Let's see this example, then you can clearly understanding all the above 5 steps. Okay, let's take as one example. Let us assume the data set X contains two features. This is the feature 1, this may be feature 2. That data set contains 1 2 3 4 records. So a simple example, two columns with 4 records. What is the first step? Standardizing the data. The mean of first column is 5. The mean of second column is 3. That means 2 plus 4 plus 6 by 8 by 4. We get in the 5. 0 plus 2 plus 4 plus 6 by 4. We get the mu t equal to 3. From the standard deviation formula, we have to calculate the sigma 1 and sigma 2. Okay. Then we have to calculate in the Z by the which one? Standardization formula. What is standardization formula? X ij, okay, minus mu, okay, by calculating which one? Sigma. Okay, maybe some mu j by sigma j. See the standardization formula. By this formula we are getting the standardization value at each and every cell. Okay, this is the standardization matrix. From this we have to calculating the which one? What's called as covariance matrix. What is the formula? 1 by n minus 1. We have to transpose this one. What meaning of transpose? Simply rotate rows into columns. Okay, so that means transforming. The transpose means this row is divided into column. This row is divided as transformed as a column. This row is transformed as a column. This row is transformed as a column. Okay, that is Z transpose. That can be multiplied with Z. Okay, then n means number of observations. 1 2 3 4 observations. That means 1 by 3. Then we are getting the matrix like this, 1 1 1 1. This is called a covariance matrix. Step 2 is complete. Hope everyone understood. From that, we have to calculate the eigenvalues and eigenvectors. Calculate eigenvalues and eigenvectors. To calculate in the eigenvalues, we have to determine the C minus what's called as lambda I equals to which one? 0. C minus lambda I equals 0. Then we have to find out which one? Determinant. What is C value? All the ones. Clear? This is a C. Okay. Minus lambda. What is I means identity matrix. This is 2 by 2. That's why lambda 0 0 lambda into 1 1. Getting like this. So what is determinant we getting? 1 minus lambda. Okay. Then 1 minus 0 equal to 1, 1 minus 0 equal to 1, 1 minus lambda. The determinant is AD minus, simply if the matrix is A, B, C, D, the determinant is AD minus BC equal to 0. This is the AD, 1 minus lambda whole square minus, this is the BC, 1 into 1, that equal to 1. If you solve this one, we are getting the values for lambda equal to 2 comma 0. That means we are getting the two values for lambda. We are getting two eigenvalues. Okay, that means if having the two features, we are getting the two eigenvalues. If we're having three features, we are getting three eigenvalues. If we're having the four features, we are getting the four eigenvalues. After getting these eigenvalues, we are arranging these eigenvalues in some descending order. Okay, already these are in some descending order. First one is lambda equal to 0. Okay, so now from these eigenvalues, we have to calculate the eigenvector. How to calculate eigenvector? C minus, okay, lambda I, okay, C minus lambda I into V equals to what's called as some 0. Okay, first we are taking as lambda equal to how much? 2. Okay, then we are getting some matrix. What is the V here? Vector. We are having V1 and V2. V1 and V2. Okay, we are multiplying these two, we are getting one equation. Okay, like that, lambda equal to 0 we have to keep. Okay, substitute lambda equal to 0, then V1 into this vector is V1 comma V2, we are getting another equation. Okay, then likewise we have to get, if lambda equal to 10, we are getting the vector V1 equals to, clear, 1 we are getting. If lambda equals 0, we are getting another vector is minus 1, what's called as minus 1. Here I am taking as the transpose. Clear? That is calculated eigenvectors. Guys, if you are not, you need little bit of linear algebra. Okay, if you are not understanding, if you are something lagging about the mathematics, simply we have to what is called as revise how to calculate eigenvalues and eigenvectors. Some example, then you can easily understand this concept. Okay. Once if you calculated eigenvalues and eigenvectors, then we have to transforming the data. Okay, so here I am considering only eigenvector v1 only. Why? Because if I want to choose only one component, that is with lambda equal to I want to choosing. That's why v equal to v1. Okay, so that's why its values are 1 comma 1. What are the first? If lambda equal to 2, what is the eigenvector we're getting? 1 comma 1. This is transpose value, but we actually we're getting eigenvector is 1 comma 1. This is the component 1 eigenvector. This is the component 2 eigenvector. Here I am choosing only lambda equal to 2 eigenvector. That's we getting 1 comma 1. So after getting this projection matrix Vk, then we have to transforming the data. How we are transforming the data now? Z into Vk. We know the standardization matrix. We know the Vk. Multiplying both, we are getting the again actual standardized data. Okay, this is, guys, hope everyone understood. This is the mathematical institutions we are having to find out the principal components. Okay, so the principal components mainly depend upon the lambda values. More lambda value means most important principal component, less lambda value, that is the less important component. That means that future may having the less important value. From that lambda values we are calculating eigenvectors. After calculating eigenvectors, then we are getting the again transforming the data into actual data by using this Z into Vk. Clear? So now that is about principal component. Okay. So now how to implement in the principal component? The principal component in implementation involves in two steps. Maybe by using SVD, that is singular value decomposer, and by using directly applying the PCA. By using the SVD in sklearn or by using the PCA class in sklearn, we are implementing the PCA. Okay, so how to implementing PCA using SVD means, first we have to find out the centered. X centered equal to, X means all the features, minus we have to calculate the mean, x dot mean, the all the features we have to the mean of all the features. Okay, then subtract it, then we are getting the x centered, then we are applying np dot linear algebra dot svd of this x centroid. Hope you get the values of u, s, v value. Clear? After that, extracting the components, how many components you have to needed from that result. I want to extracting only two components, so all the records, okay, from the data set I want extracting only how many components, two components. So I want extracting the number of principal components. After extracting the number of components, then we have to converting that what's called as projecting that one into actual transforming the data into normal data. Okay, that is we are getting by x centroid into dot of which one, wd. That means we have to transforming into the data actual data set. This is the implementing PC using svd. Directly we're having the PCA class in SQL. From that also we have to implementing the PCA. So PCA equal to I having one hyperparameter n components equal to 2. That means it can pick the only two components from the entire dataset features. Then we have to transforming by applying the function fit underscore transform of which one x. Okay. Then we are getting the which one x to d. Okay, so we get the principal components. Okay, so by that principal components we're choosing the two components. Okay, so from those two components we have to fit transform applied which one actual standardizing the data. Then we are getting the transformed data set, getting the transformed data set. Now here the main question is, okay, how many principal components are uh, needed, okay, to the entire data set. So let us take the scenario. That means, for example, we are having n equal to 100 features, n equal to 100 features. For example, I am choosing the number of components equal, for example, 3. Out of 100 features, if you are choosing the only 3 components, that means the remaining 97 features we are neglecting. That means if you are neglecting the more number of features, there may be chance to lose the actual data in the training data. Okay, that means we may what's called as we may lose the actual data, okay, from the given data set. Okay, so without losing the actual data, without losing the actual data of the given data set, we are trying to finding the optimal number of components, optimal number of components. Okay, so for that here we are using one component called as explained variance ratio variable. Explained variance ratio variable. This should be helpful for choosing the how many number of components are, okay, how many number of components are uh, needed, or how many number of components are best to the given data set. That should be find out by using this variable. Clear? For example, here I am choosing the, for example, two components. The first component variance ratio is 0.84. The second component variance ratio is 0.14. Okay. So that is here PC dot explained variance ratio. So if that explained variation ratio is more, means that is important uh, component. It is less, means that is maybe some less important component also. Okay. So now, for example, the PCA we also implemented a number of components equals to, if I am passing from 1 to some 2, 3 something, it can extract that many number of components. If n components value is 0 to, for example, 0.95, what does it mean? Or if we are giving the value in n components is from 0 to 1, means this value can be taken as explained variation ratio. What this indicates means we have to pick the number of components. We have to pick the number of components. That number of components covers 90% of the what is called as actual data from the existing given data set. Okay, so hope you understood. For example, let's say we are having 100 features. From that 100 features, we can pick the only, let us assume, 3 components. By choosing the 3 components from 100 features, that means we are neglecting the 97 features. We are neglecting 97 features, maybe some 50% data may be lost. Okay, if you lost the 50% of data, that means if you try to building the model may not be give the better performance. Without losing the data, we are trying to finding the features. So for that purpose, we need to identify what is the optimal number of components are needed for the given data set. The optimal number of components to the given data set without losing the data. For that, this explained variance ratio value is helpful. Here what tells to the data set means we have to pick the number of components. Okay, that components covers 90% of data having the match with the actual data set. Match the actual data set. Okay, that is the meaning of this 0.95. After getting the number of components, again we have to transforming the data. Okay, PCA dot fit transform of which one? X transform. This is the most important to pick the number of components. Okay, so now again one more thing is, okay, so take the number of dimensions in X ratio. Explain variance is some another y-axis. Okay, if we are choosing the dimensions, explained variance ratio may be increasing like this. More explained variance means, okay, 50 dimensions we are getting the ratio may be some 0.8. For example, for 150 dimensions we are getting maybe some 0.95 variance ratio. Maybe some after 200, maybe some 300 we are getting explained variance ratio is 1. But 150 ratio will cover the almost 95 percentage of data. 95 percentage of actual data. That means we may lose only some 5% of data. That may not be negligible if you're considering some lakhs of records. Okay, so from the elbow method, okay, we have to, by this diagram, what observing means, maybe some, what we can see that maybe some at the 150, for example, we are having 400 dimensions in our data set, 400 features, but 150, if you are considering 150 features, we may get the which one? 0.95 explained variance ratio. That means we may getting almost actual original data with 150 dimensions only out of 400 dimensions of the actual data set. That for that purpose this diagram is helpful. Okay, that means for example, MNIST data set contains 28 by, okay, 28 by 28 size pixels. That means we're having 784 features. If you're reducing this 784 into, for example, number of components equal to 154. Okay, let's see, this is the, here I am considering how many components? 154. Actually how many features we are having? 784. But how many components I am choosing here? 154. If we are choosing the 154 components from these 784 pictures, we are getting almost all actual data. This is the original data set 27853. This is after considering the 154 components, we are also getting the same data. Okay, that means how we are getting the data with 784, the same data also we are getting with the 154 features with the help of which one? PCA. Like this we have to compress, or that means we have to choose the, like this we have to reducing the dimensionality of the which one? Data set. Okay, the advantages of PCA is main helpful for dimensional reduction, improve the model performance. When we are reducing the dimensionality with the less time we have to train the model, it helpful for improving the performance of the model. We can easily visualizing the data with a fewer number of components. Okay, uncorrelated features, produce the principal components that are linearly uncorrelated, and simply we can analyzing the features. These are some of the advantages of PCA. Okay, okay, that is about the PCA.